Have you ever stopped to think about what actually happens the moment you connect your computer to a network? You plug it in, and seconds later, you're online. It feels like magic, right? Well, it's not magic. It's a really cool high-speed negotiation between your device and the network's router. Today, we're going to pull back the curtain on that process, specifically for IPv6, and look at the two main ways it gets done, SLAAC and DHCPv6. So that's the big question, right? How does a device which knows nothing about the network it just joined get that all-important global IPv6 address? This isn't a trivial thing. It's a dynamic process that has to work perfectly every single time to get you online without causing chaos. So let's follow a device on its journey from a complete newbie to a full-fledged member of the internet. Okay, first things first. Before a device can even think about talking to the outside world, it needs a way to talk to its immediate neighbors. A really key concept in IPv6 is that every single device actually has two vital addresses, and each one has a very different job. On one hand, you have the link local address, or LLA. Think of this as a device's local private nickname. It's only used for chatting with other devices on the exact same physical network link. Your computer generates this automatically the second it boots up. It always starts with FE80, and it's absolutely essential for basic network chatter. But that address can't get you on the internet. For that, you need the main event, the Global Unicast Address, or GUA. This is your public passport to the world address, and how a device gets this address is what we're here to figure out. So, just to lock it in, the link local address is automatic and strictly local. It lets your computer talk to the router right next to it. The Global Unicast address, on the other hand, is for the big, wide internet, and it is not automatic. It has to be assigned, and that assignment process is what we're about to dive into. All right, so our device has its local nickname, its LLA, but it's still stuck on its own little island, completely isolated from the internet. To get its global address, it has to do what any of us would do in a new place. It has to ask for directions. It needs to find a router and start a conversation. And this right here is that first conversation. The host basically shouts out a router solicitation, an RS message, to a special address that only routers are listening to. It's like yelling, "Hey, is there anyone here who can get me to the internet?" Any router on the network that hears this will reply with a router advertisement, or RA. And this RA message, this is the golden ticket. It contains everything the host needs to know, including the network prefix and a set of instructional flags. Now, those flags we just mentioned in the router advertisement are incredibly important. They aren't just suggestions. Think of them as direct orders from the network administrator, configured right on the router, that tell the host exactly what it needs to do next to get its address. It all boils down to these three little on-off switches. First, you have the A flag for address auto-configuration. If this is switched on, the router is saying, "Go ahead, you have my permission to make up your own address." Then there's the O flag for other configuration. If that's on, it's a hint. You'll need to get other info, like DNS servers from a DHCPv6 server. And finally, the big one, the M flag for managed. If this switch is on, it's an undeniable command. Stop. Do not create your own address. You must get one from a server that manages them. The way these three flags are set creates this perfect decision tree. It guides the host down one of three very specific paths, and these paths fall into two main categories. You have stateless, where the host is pretty independent and makes its own address and no server really keeps track of it. And then you have stateful, where a central server is in complete control, managing and leasing out addresses and keeping a detailed record, or state, of who has what. Okay, so let's walk through each of these three paths. We're going to see exactly how a host follows those flag instructions to get its global unicast address and finally join the internet. Path 1 is the most common and the simplest. It's called SLAAC, which stands for Stateless Address Auto Configuration. This happens when the A flag is on, but O and M are both off. The router's advertisement gives the host the first half of the address, the 64-bit network prefix. Then, the host is responsible for generating the second half, its unique 64-bit interface ID. It just stitches them together and bam, it has a full 128-bit IPv6 address. It's stateless because no server had to approve or track this address. So you might be wondering, how does the host come up with its half of the address? Well, there are two main ways. The classic way is called EUI64, where it takes its own unique 48-bit hardware MAC address, does a little trick to stretch it to 64 bits, and uses that. But The more modern, privacy-focused way, which is the default in most operating systems now, is to just generate a random 64-bit number. This is way better for privacy because it means your unique hardware ID isn't broadcast all over the internet. But before it starts using this brand new, self-made address, the host performs one last crucial safety check. It's called Duplicate Address Detection, or DAD. It basically sends a message to everyone on the local network asking, hey, is anyone else using this address I just made up? If nobody answers, it knows the address is unique and good to go. If someone else replies, it means there's a conflict and the host knows not to use that address. All right, on to path number 2. This one is a really cool hybrid approach. This happens when both the A and the O flags are on. So the host still builds its own IP address using SLAAC, just like we saw before. But that O, or other config flag, tells it, hey, you're not done yet. You still need some other info, so go find a DHCPv6 server and ask it for things like your DNS server addresses. The server provides the other info, but it doesn't assign or track the IP, which is why it's still called stateless. And finally, path 3, stateful DHCPv6. This is the most controlled, most managed approach you can have. Here, the M, managed, flag is on, and the A flag is off. The router is telling the host in no uncertain terms, do not make up your own address. Your job is to go find the DHCPv6 server and request everything from it. Your full IP address, your DNS info, the whole shebang. The server then assigns an address from a pool it controls and keeps a stateful record of that lease, a lot like how DHCP works in the old IPv4 world. So there you have it, the 3 distinct journeys a device can take to get online with IPv6. Let's just put it all together in one simple table, and then the fun part, I'll show you how you can figure out what's happening on your very own network. This table really pulls it all together, doesn't it? You can see the clear trade-offs. With SLAAC-only, it's super simple and decentralized, but you don't automatically get DNS info. Stateless DHCPv6 solves that. You get the easy auto-addressing from SLAAC plus the centralized DNS info from a server. And finally, stateful DHCPv6 gives the network admin total control, which is often what you want in a corporate environment. And it all comes down to how those simple A, O, and M flags are set on the router. And now you can actually apply this. If you're on a Windows machine, pop open a command prompt and type ipconfig/all. Go find the section for your network adapter and look at your IPv6 address. Now you have the tools to be a detective. Does the address look random? Or does it maybe have that FFFE in the middle suggesting it's from your MAC address? Is DHCP enabled? Based on everything we just talked about, you should be able to figure out exactly which method your network is using. So the question I'll leave you with is this: which of these 3 paths is your computer on right now? Go find out.